Thank you very much, Simon, and good afternoon, everyone. I have the pleasure of talking to you a little bit over the next 45 minutes or so about automated mobile robots, autonomous mobile robots, industrial robots, and combinations of those. As Simon said, we'll deal with any questions you have at the end of the presentation, time permitting. So I'm going to run through first of all just a handful of some of the key definitions that are appropriate to our topics, uh, and then I'm going to look at some statistics from the International Federation of Robotics. Um, just to give us some background about uh, where robots are used, which parts of the world they're being used in great numbers, and which sort of applications. Uh, it, it's it is just to give us some general understanding of the growth that can be expected and the areas of growth that are being predicted. It is an area that we are, of course, seeing significant growth in with the increasing needs of automation and so on. But then we'll look at some examples of the use of AMRs, autonomous mobile robots, and examples of the use of robots working collaboratively, robots in collaborative applications. And then we'll look at very, very important consideration that we need to have in mind how we ensure that these type of applications, autonomous operation, collaborative applications, and so on, how they can be performed safely without exposing people around them to an unacceptable level of risk. And we'll look at the technologies that are being used on autonomous mobile robots, and we'll finish by looking at how that applies to robots being used in collaborative applications. So those are our topics for the next hour or so. Um, so some definitions. An industrial robot, and we're talking about robots that are used in industry. Uh, our main topics today are all about robots used in industry. We're not talking particularly about medical robots, service robots, and so on. So an industrial robot is quite simply a reprogrammed multi-purpose manipulator that has three or more axes. And they come in all sorts of different shapes and sizes, and are used in a huge variety of applications. So it's difficult to be too specific about the, the whole variety of applications we have. But what is of growing importance and growing relevance is the use of robots in a collaborative application. So a collaborative application is defined as an application that contains one or more collaborative tasks. So a blindingly obvious definition, I guess. So the key to it is a collaborative task. And a collaborative task is a task where that involves the use of a robot, but a task where a robot and an operator are within the same collaborative workspace. So working without physical separation between the robot and people. Traditionally, of course, industrial robots have been used where they would be enclosed in physical guarding and very, very often called robot cells. The robots would be only accessible by people entering the danger zone, the zone where the robots are, by monitored movable guards or some other measures like that. Collaborative applications are where we're going to acknowledge that there will be people and robots in the same zone, so they could come in contact with each other. So that's the important thing. And AGVs and AMRs and IMRs, the terms are used slightly differently in some cases. Um, we shall look a little later at a North American standard that has tried to put some fairly precise definitions on the use of these abbreviated terms. But in essence, an AGV is an automatic guided vehicle that follows fixed routes. So they would typically be following a route mapped out and using inductive guides embedded in the floor or something of that nature. So they could work only along the tracks that they've been assigned to. Um, and there is a place for those, of course. They've been used very, very successfully for many years, and there's still applications which suit that kind of approach. But what we are seeing more and more, and because of the increasing use of more advanced technologies, is mobile platforms, mobile vehicles that don't have to follow a fixed path, that can navigate by the use of various sensors and various technologies, um, and so they can move around dynamically, and you know, in some cases, if it's particularly if it's an outdoor application, they'll be using GPS systems or this kind of thing to map their routes, but they're working autonomously. Uh, so those kind of platforms are more likely to be described as an AMR, an autonomous mobile robot. Um, and safety has to be assured, of course, so we'll look particularly about what sort of technologies are used to ensure that the AMRs can be deployed safely. And an IMR, an industrial mobile robot, is a combination of an AGV or an AMR with an industrial robot mounted on the platform. So it's a combination of the two types. We'll revisit those terms a little later when we talk about the North American standard that deals with these topics. Those are some of the key terms. AGV and AMR, I think, tend to be used interchangeably, really, but AMR is, for current technologies, is arguably the more correct term. Um, so robots have been around now for a very, very long time, 50 years or more, since the first robots that could truly have been described as industrial robots were used, primarily in the automotive sector, um, but their growth has been relatively consistent. In the early years, the use grew quite rapidly until there was an incident in a painting application in an automotive manufacturing plant in Dearborn in the USA, where the robots decided to go a little bit crazy, if I could use that expression. And some windows got broken, some physical damage was done because of this random operation, and it set back the deployment of industrial robots for a few years. But then the technologies, the control technologies improved. The chances of those sort of things happening again were lessened, of course. So they've started to be wider and wider use. And this slide on the screen now is from a report from the International Federation of Robotics, and they produce a report that looks at the deployment of robots throughout the world. And we can see that from the years 2009 up to 2018, there was steady growth. Um, it was knocked back, of course, because of the pandemic, which knocked everything back. So 2019 saw a drop in the annual installations, but we see that there was um, clear and steady growth for the years before that, and that growth is expected to return. Um, this slide now, this graph shows us the percentage of installations according to the three key regions, Asia and Australia combined, Europe and America. And I'm not sure how much Australia counts for in the blue bars on this graph, but I suspect it's a relatively minimal amount. So I think what this shows us beyond any doubt is that the key growth areas are in the Asian market. That's where we're seeing the greater density of robot installations and the greater take up of various technologies. USA is showing as less density than Europe, which some may find a little surprising, given that historically the USA has been at the forefront of these things. So it's Asia. Asia are the key areas where we're seeing the greatest growth. And this shows the main application areas where robots are deployed during the last 3 years, 2000, or the 3 years 2017 to 2019, from this 2020 report. And you can see that the largest number of robots are used in handling applications. So part manipulation, pick and place robots, all of those kind of applications. And once again, we saw that there was a decline in 2019, not a massive decline, but there was a decline in 2019. Welding is the next largest application range, and again, there's historically robot welding has been a very, very significant area, and I think this shows us that it remains a fairly significant area of the use of industrial robots. And then the rest are lesser volumes, assembling, clean room dispensing, processing, and so on. So it's still handling and welding robots combined that are the huge areas for industrial robots in particular. And the importance of manufacturing robots is shown in this prediction here. Again, it's from the same report sorry, not from the same report. It's a different report, my apologies, from the DigiWorld report of robotics, showing the predictive growth in by applications, and the two big ones are manufacturing robots and logistics robots. So they're the sort of things that are used in industry, in manufacturing and commercial applications. The use of health robots is growing, but they don't have anything like the same volumes, and the other areas, agriculture, business, service robots, domestic robots, again, are accounting for the top of the columns there, but the big columns, the big blocks are manufacturing and logistics robots. And that's where we see industrial robots and AMRs, AGVs, IMRs are in those two sectors, manufacturing and logistics. So some examples where we would see autonomous mobile robots. The next few examples are taken from press releases by different organizations. So Faurecia, tier 2 supplier in the automotive sector, are deploying AMRs from a company called MIR. And on the screen now, we can see that there are three particular types of application that use AMRs. The one in the middle is transporting around a rack, um, something that stores components, so it can deliver components to machine locations, deliver and collect components from racks, and carry the racks around to different areas. The one on the left is a mobile conveyor section. So that could be deployed at robot conveyor sections to help with the flow of products, and could increase flexibility by being able to simply redeploy the small conveyor, transfer conveyor section, whatever it is, to a new location. Very, very straightforwardly. And the one on the right is an example of an IMR, an industrial mobile robot, where on an AMR platform there's a robot manipulator mounted on the platform. So that's the typical example of where you could have a handling robot, a robot perhaps doing some basic machining tests and so on, that can be moved around from position to position. There was one study conducted quite a few years ago now, which was using those sort of combinations, a robot on a AMR platform in the aerospace sector, in aircraft body manufacturing, and that project was to try and bring principles that have been developed in automotive manufacturing into the aerospace sector, and they were using the IMRs to do the riveting and fixings on aerospace structures. So those are, say, some examples showing three typical tasks that would be carried out by mobile platforms. Another clip from a press release about Skoda, and they're using Omron's logistics robots. So in the center of the screen there, we can see a robot manipulator, an AMR, autonomous manipulator, carrying parts from machine section to machine section. But above that, there is what is a combination of a manually operated forklift truck that has been also equipped for autonomous operation. So it can function both as a traditional manually driven device, or it can be operated autonomously. So combinations of manual and autonomous operation. I guess it won't be a surprise to anyone to know that a very large user of AMRs is Amazon. Amazon have got a very, very active division, more than a department, I think, operating in various parts of the world for deployment of advanced robotics technologies, and understandably, a big part of that is their AMRs that move those product storage racks around the warehouse floor. And you can see from the picture on the right there that those racks are very, very tall. They can be quite weighty, very, very heavy, and the AMRs have to operate very, very smoothly. Otherwise, there would be the danger of them toppling over and so on. So the basic warehouse floor structure becomes also critically important to make sure that they have a smooth operating plane. So those are some examples of the deployment of AMRs. AGVs, AMRs, they are growing in use exponentially, and they're extremely effective at the sort of things they need to take the humans out of the picture, make sure that these relatively simple tasks of moving product from one position to another are done with autonomous mobile robots. Another area which is again of growing importance, we're seeing more and more deployment, is in what are generally simply referred to as cobots, an abbreviation of collaborative robots. My personal preference is that we emphasize the fact that these are robots being used in collaborative applications, and not all applications, we'll revisit this in a few minutes again, but not all applications that are developed for the using these so-called cobots are suitable for collaborative working. Um, so the use of the word cobots has become universal. Everybody talks about cobots, but it is extremely important that we consider the application, which we'll come to in a few minutes. So here's a universal robot, a UR robot, being used in a machining application. So it's clearly it's the manufacturing of engine blocks. So there's an engine block there, and the end effector on the UR robot has got some, looks like some drilling attachments. So it can be doing some drilling and tapping tasks on the engine block itself. Um, Machine loading is again a huge area where the we have collaborative operations, collaborative tasks between robots and humans, machine tending, machine loading. Um, it's a dull, repetitive task where the human can be replaced by a robot. And I think it was one of the original, as far as I can recall, one of the original promoted areas for collaborative applications. And this is a FANUC robot that is being used as part of a cell to aid with inspection. So the precise inspection is aided by having very accurate positioning from the robot, but it's operated collaboratively. The robot is in a fixed position, um, but there's a person loading the sample in showing this picture is obviously in the same work zone, the same collaborative workspace as the robot. And those applications we've just seen are clearly they're industrial applications, and that's where we're seeing the huge growth, huge deployment. But robots that are designed for collaborative applications don't always get used in industrial settings. In fact, this is an example of the use of a pair of robot arms that are deployed as a robotic chef. And this is a real application. This isn't made up. You could type robotic chef or Moby Robotics into a search engine and see videos of this in operation. It can reproduce meals for you. It comes as part of a robotic kitchen, um, and it's a very novel application. It is, despite the looks of it, with all the stylized bits on it, that is a pair of universal robot arms configured to replicate the actions of a chef. Lots of safety features built into that, I have to say, but that's an example of an application using these typical industrial style robots, but in a non-industrial environment. So it is, of course, extremely important that we ensure that people working in and around these AMRs, IMRs, collaborative applications, and so on, are protected from the possibility of harm, protected so that they are not going to be exposed to an unacceptable level of harm. And in an AMR, that's done by combinations of sensors. And this is information taken from the MIR Mobile Industrial robots company in Sweden about their systems, and I guess their primary level of protection is using area scanners, laser scanners, area scanners, active optoelectronic protection devices that are two-dimensional uh, devices that can scan a field um, and they're programmed to scan various areas around them. They typically have a 270-degree area that they can scan. So they would be deployed perhaps on two corners of an AMR, and between a combination, you've got 360-degree coverage covering all sides of the device, and they're programmed to say that if there's an obstacle in the path, it will be detected by the scanner, and action can be taken by the AMR to either simply saying, of course, it's just a stop, but they could also have onboard systems that would allow them perhaps to dynamically change the path so they can go around the obstacle. So all sorts of varieties of things that um, could be configured for being triggered by the area scanners, the laser scanners. But they also include combinations of camera-based systems that are three-dimensional. The area scanner, by the way, is a two-dimensional device. Um, by the use of 3D cameras, you can get a more uh, comprehensive picture of the area surrounding the AMR, and that can also be used as part of the safety monitoring system. And then, as the final picture on the right there shows, they can have sensors that are looking down from the overhang of the platform down to the floor level, that can detect if it's detect the feet of people or other objects that would be below the range of the laser typically. So a whole range of different technologies that are combined to be used together to give us an adequate level of protection. An adequate level of protection generally means that to conform to the international standards for robotics, the safety related parts have to meet a clearly defined performance level with a defined architecture. And the two standards that are stated within the robot standard. The robot standard, by the way, is ISO 10218, which is in two parts. 10218 Part 1 is for robot manufacturers, 10218 Part 2 for the applications of robots, integration of robots. And those standards require that the safety related parts need to meet if we're looking at the requirements of the functional safety standard ISO 13849, which is being referenced on the table on the screen now. They have to meet performance level D with category 3 architecture. The other standard we'll see in a few minutes is an IC standard called 62061. So you can see that, again, this is information from MIR. With the exception of their very small, low-risk devices, all of the safety functions on their larger platforms are designed to meet the requirements specified in 10218. So they're all capable of performance level D, and they've achieved that by the use of category 3 architecture. A little bit more about that in just a few minutes' time. But some of the technologies that are used in combinations. As we saw, on an AMR, we perhaps have a combination of two-dimensional laser scanners being used with 3D camera technologies and so on. And these things need to be combined in in a way that ensures that we're meeting the requirements for risk reduction provided by the control functions. And a laser scanner, also called now PDDR, are established technology. They've been around for a long, long time. They're well understood. They're used in lots and lots of different applications, not just in mobile or autonomous applications. They're used in fixed installations and so on. But there is an increasing use of emerging technologies being used in the field, where things like radar and LiDAR are being used as giving making a contribution to the overall safety. So not just relying on traditional approaches, but using combinations of different sensors. And that has led to the development of specific publications from standards bodies to try and give some clear guidance about how to combine these technologies. So the functional safety standards, the two at the bottom left of the screen now, ISO 13849, IC 62061, are the two standards that cover functional safety for machinery applications. AMRs, IMRs, and collaborative applications are within the scope of those standards. The generic standard for functional safety is a standard called IC 61508, and both 13849 and 6061 have a relationship with 61508. But the combination of sensors that can be used to meet the targets specified from those functional safety standards is now assisted by a publication of a technical specification called 62998, where that gives some guidance on the deployment of various sensor technologies. And on the right hand side, we've got some standards that are relevant to sensor technologies. The use of sensors developed that are going to be used in safety applications, how they can be combined to give us systematic safety capability that can then be demonstrated to meet the requirements of the functional safety standards. So 62998, if you like, provides the link between the sensor standards and the functional safety standards. 62998 is in two parts, where part two is actually a worked example of an outdoor AMR, based on an outdoor AMR, how different sensor technologies have been used to create the appropriate levels of systematic safety integrity. For collaborative applications, again, this is covered in 10218. 10218 has got specific requirements about collaborative applications, and it describes 4 separate types of collaborative application, where the first one is called a safety-related monitored stop. We'll see a little bit more detail about these 4 immediately following this slide down. The second is using something called hand guiding. The third method is speed and separation monitoring, which has got some correspondence to the first method. And the fourth method is power and force limiting. And of these 4 methods, I think the one that was most likely to be being looked at in practice is power and force limiting. So just briefly a word about these 4 separate methods that are used in collaborative applications. So safety-related monitored stop, the example shown here are using area scanners. Again, typical use of an area scanner, where showing the graphic here is showing that there is a robot that is protected on two sides by physical guarding. So there's a physical barrier between people and the robot, but the other two sides are open, but are being monitored by an area scanner, a laser scanner. And that scanner would be programmed. It could be programmed with different zones and can do a lot of more advanced things like zone switching and things like that. But in the graphic we've got on the screen now, typically the red zone would be a trip zone. So if there was anything detected in that red zone, we would get a safety rated monitored stop from the robot. The robot would go to a standstill and would remain at a standstill, and it's confirmed until it's confirmed that the area is clear and it could go back to normal operation. That principle has been well established and has been used in applications where the robot itself wasn't necessarily designed for collaborative application, because in that, although it's an unprotected workspace from a physical point of view, we can't have people and the robot in the same area at the same time whilst the robot is capable of moving. Hand guiding is a case where typically used for teaching the robot, teaching a robot's path, where the robot is allowed to have some power to the robot actuators while somebody is in direct contact with it, as we can see in the picture here. And so the teacher of the robot, the operator, is now perhaps going through a routine where he's teaching the robot its path. The robot may have been deployed to a new position, gone to a new machine or whatever. So he's running it through the path that it would need for this specific application. And whilst that's happening, there have to be other measures in place. The robot would only be allowed to move with a safe limited speed. There has to be an enabling device. An enabling device is sometimes the term used for an enabling device, a dead man's handle. It's typically a device that is a handheld device that has to be held in a mid position. So if you release it, the enable is removed. If you grip it tightly, the enable is removed, that type of thing. So, and once the enable is removed, the robot has to stop. And there also has to be a local emergency stop deployed in the area as well. So, but the robot has power to the actuators whilst it's being guided. The third application, so this is a sort of a combination of separation monitoring and safety rated stop monitoring, where we have some, again, area scanners are typically used to provide this kind of, this particular kind of protective arrangement, where if someone is getting closer to the robot, going into the orange zone, the yellow zone, as we can see on this slide now, the robot will reduce its speed, perhaps give a warning, and then if you get too close, it will go to a stop condition. So it's got quite a lot in common with the first methods, safety rated monitored stop. But the fourth method is arguably the most common and comes with perhaps the most concerns, which is power and force limiting. So in this method, it is acknowledged that robots will be operating normally whilst people are in the vicinity, whilst people in the collaborative workspace. So it is acknowledged that there is a possibility, quite a strong possibility, I dare say, that the person and the robot will come together at some point during the operating cycle, whilst the robot is operating. So what's needed here is to say that if that happens, or perhaps it may be more correct to say when that happens, the power and force delivered through the robot, including its end effectors, the tooling that's mounted on the robot, has to be sufficiently controlled to ensure that an unacceptable level of pain isn't inflicted on the person. So this brings about a concept which creates a reasonable amount of concern, that we're saying, okay, we're going to accept that a person can come into contact with a moving part and can be subject to direct contact, can have some force from the moving part before the moving part needs to stop. So again, this is described, the basic concept described in 10218, but the detail about how we go about ensuring that things are safe is contained in a technical specification. It's TS 15066, where a study was carried out at a German university, the University of Mainz, where they exposed people to various points along their body. As you can see, there are 29 specific body areas where they monitored people with what's called quasi-static contact. Could be described as a crushing force, a crushing hazard, being trapped between two moving parts or between a moving part and a fixed part, and also for transient contact, where the moving part of the robot would hit you, but you would be knocked out of the way. For example, it wouldn't draw you in, wouldn't crush. So the result of this study was that they came up with some acceptable force limits depending on which part of the body is likely to be exposed. And these force limits, say, are published in the TS 15066 in a table. This is the top part of the table, as you can see, and you can see that there are maximum allowable pressures in newtons per centimetre squared in the quasi-static column there, and maximum force in newtons, and the allowance for transient contact is twice the force, twice the pressure as for static contact. So this needs very, very careful setting up, very careful consideration, and ensuring that these targets are being met does need specialized equipment, and people have to be trained, obviously, and competent in the use of that specialized equipment. You can see that the top of the thing there, the critical zone, is not allowed for transient contact. So face and skull and forehead is typically you wouldn't rely on power and force limiting. You mustn't allow on power and force limiting to reduce the risk associated with that area. It has to be more traditional protection taken account of if that's the risk. And what this means is that we have to work on the assumption that even if something is called a cobot, it's designed to be used in collaborative applications, it doesn't mean it's automatically safe to use alongside workers. We still have to ensure, we must ensure that people aren't exposed to an unacceptable level of risk. So a robust risk assessment is vital. And I'm sure a lot of you listening, if not all of you listening, will have seen the news last week where in a robotics chess game, the human opponent had injured their finger. I think it's been described as broken finger. I'm not quite sure of the true details of this, but a cobot being deployed as a chess player actually grabbed the finger of their opponent. And I think what is clear out of that is that the a robust risk assessment had not been carried out here, that the end effector, the grippers were not designed suitable for the potential that they could grab somebody's finger. The power and force exerted was not limited, and so on. So I think the key thing that went wrong here is that the guidance about task-based risk assessment and necessary measures wasn't correctly employed. So a few moments ago I mentioned that the safety-related controls for all of these things, for the 4 ways of protecting collaborative applications and for all other aspects, autonomous mobile robots and so on, need to meet. Sorry, my screen has just changed for some reason. I know. Okay. I don't know. I'm sorry. I'm dithering here because it seems to me as though the attendees are no longer seeing my slides. They've come back. Perhaps that was a transition. I don't know. Anyway, the 10218 describes currently this standard is due for change. It's overdue for change, I might say. So some of these aspects might be slightly different in the next version of the standard. But I mentioned it briefly a little while ago that the safety-related parts have to meet performance level D with category 3 architecture if we're working with 13849, or SIL 2, safety integrity level 2 with hardware fault tolerant 1 if we're using the IC standard, the IC 62061. What that means is that we have to be able to demonstrate that the safety related functions have got a suitably low probability of dangerous failure, quantified down to very, very small probabilities, and that we have redundant architectures in our controls. So we have 2 separate channels in our safety ready controls, each channel being capable of providing the safety function. The standard that I referred to, the American standard I referred to right at the beginning, was developed by the Robot Industries Association, which have now changed their name to AS3 or something they call themselves now, but in conjunction with the with ANSI, the American National Standards Body, and they produced a standard part of their R15 series, R1508. It's 18 months old or so now, a little more than 18 months old. But this standard was set out to fill a gap where the traditional standards for AGVs, for driverless trucks, one of the titles in one of the standards, wasn't really up to date with the growing deployment of AMRs and IMRs. So in this standard, that's where they came up with these definitions of IMRs as 3 different types, type A, B, and C, where an IMR type A is an autonomous mobile robot. That's the mobile platform only, something that moves racks around, moves fixtures around, and so on, as we saw in an example earlier. A type B is an IMR type A with an attachment, but a passive attachment. So the example we saw earlier with a conveyor section on an AMR would be a type B in this by this definition, and a type C is an AMR or an AGV that has an industrial manipulator, so a true industrial mobile robot. The standard does give us some clear guidance about how we can make the choice. These flowcharts now summarize the way we would go about checking whether we should consider something to be a type A, a type B, or a type C. It had been intended, or maybe still is intended, that this will also be the basis of a new ISO standard, a truly international standard. But I'm not sure exactly where that work is. But if we're looking at deployment of these things, this particular publication, 1508, does give us some very, very helpful guidance. And that really brings me to the end of the topics. This final slide here is again is copied directly from the IFR World Robotics Study, where their conclusions, their summary was that there are still many what they call 4D jobs, dual dangerous, detected, dirty jobs, tasks that it can be done by robots. So it brings improvements to worker health, job satisfaction, and so on. We are living in aging societies, and that means a workforce, an aging workforce, simply doesn't have the physical strength that a younger workforce has. And there is exponential, I think it's not entirely untrue to say, exponential growth in technology, going with smart manufacturing, whether we call it smart manufacturing, Industry 4.0 or whatever. These things we are seeing much more of it, and strong arguments say that we get a good return on investment by using robotics, and more flexibility in our production layouts, smaller carbon footprints, and so on and so on. So that's it as far as my presentation is concerned. So I think we do have some questions. So I'm going to hand back to Simon for questions.
Okay, we did have a little bit of a glitch, but I think we may have some here. We've got one question. You mentioned ISO 10218-1 -2 for industrial robots in the context of AMRs. Did you mean to refer to ISO 3691-4?
3691.4 is driverless industrial trucks. Both of those standards refer back to functional safety standards, and I think David is. Good afternoon, David. By the way, nice to hear from you. I hope I didn't make a mistake, David. I may have done, of course, but I think it was when I was looking at the MIR, the MIR table, where they're referring to the requirements for their AMRs, relating it back to 10218, where they were saying PLD Cat 3, according to that requirement taken from 10218. That was my thought process. Whether I said it completely correctly or not, I can't be sure. But thank you for pointing it out, David.
Okay. The next one is, how is the performance of radar and LiDAR systems verified to meet a specific PL level, considering they would only have a limited coverage?
The approach taken is to help inform the systematic capability, and we're talking they're deployed. What's happening in reality is that radar and LiDAR are also being used in autonomous vehicles, and the way that they're being deployed in autonomous vehicles, those techniques, those principles are being picked up for some applications of AMRs and IMRs. And what 62998 sets out to do is to set out a path where you can evaluate the systematic capability of the sensors, and then come up with the systematic safety requirements of the systems that are going to deploy the sensors. So by using a combination of different technologies. So the coverage is of course important, and ensuring that they will typically only be being used for things that were close enough, being detected close enough to the AMR, the IMR, to be able to give a reaction to protect the people.
Okay, so we've still got a number of questions, but what we will do now, we've run through a couple of questions, but that does conclude our event for today. The remainder of the questions will be sent to the attendees in the next 2 to 3 working days. But as mentioned earlier, we will be sending a copy of the presentation and recording. A very big thank you to Stuart for his timing and in his presentation. For more information, please visit our website at www.toughsud.com and send any inquiries to info@toughsud.com. But on behalf of myself, Stuart, and everyone at ToughSud, we would like to thank you for your time today and joining today's webinar, and hope you've enjoyed it, and enjoy the rest of your day. Thanks,
everyone. Good afternoon.